EC 201, lecture 19. Yesterday we saw the following biasing arrangement, where the basic idea is to compare the drain current of the MOSFET to some reference current and apply corrective feedback at the source of the MOSFET. The gate is assumed to be fixed to some bias voltage which we have really no control over, and the idea is to control the gate source voltage by varying the source voltage and keeping the gate voltage fixed. And for negative feedback, how would we determine the signs on the op amp? Okay, break the loop. Alright, so I break the loop maybe here. Apply the yank up one side of the loop. Let me choose some arbitrary signs for the time being. At this point, signs are arbitrary. We go around the loop. If we find that there is negative feedback with these signs, we're all done. On the other hand, if we find that it's positive feedback, we need to go and interchange the signs. Is that clear? So if I yank this node up, what happens at this node? Increases. Very good. If this node increases, what happens here? Increases or decreases? Increases. Why? So if the source node goes up, the gate source voltage is going down, which means that the drain current of the MOSFET is reducing, which means that there is more current flowing into this node than is being sucked out of this node, which means that this voltage will increase. Is that clear to everybody? So what is the conclusion? The conclusion is, with this particular choice of signs of the op amp, the feedback loop is actually a positive feedback loop, and therefore to make this a negative feedback loop, what we ought to do is to flip the signs of the op amp. So we derived the circuit yesterday, and today we saw that if the circuit was presented to you, you should also be able to put the signs on the op amp. In this way, if we choose Vref to be greater than or equal to Vb minus Vt, this ensures that the transistor M1 is operating in saturation, and the drain current of the transistor is Iref. So this is the circuit for the operating point. We need an incremental circuit which does this. Please note that we are trying to get gain. Alright? So we need an incremental circuit which looks like this. So any suggestions on what I might do to make, what all I should do to this circuit to make it look like this for incremental signals? Okay, one thing is, what do we do? First thing we need to look at is what all are there in the incremental circuit that are not there in the circuit on the left. So then we add all that stuff. Then we have to look at what we have and then see what all is there in the circuit that sets the operating point, which we don't want. We need to get rid of that stuff. The first thing that we need to do is add RS. Okay, so we need to generate VB. One simple way of generating VB would be to simply, we need to generate some battery voltage. One easy way to do it would be to use a potential divider. So this is RA, this is RB. The voltage at the gate is VDD times RB by RA plus RB. The VB generation is taken care of. We need to add VS and RS. So what do? Infinite capacitor and VS RS. That takes care of this part. Now the next thing to do is to take care of RL. Okay, so any suggestions on what I might be able to do? One suggestion is, at the drain you connect RL through an infinite capacitor. So the suggestion was to use an infinite capacitor and put RL. Okay, so that takes care of this guy here. So what else? Are we done or what? What is annoying you here? The difference between this chap and this guy is that incrementally the source is grounded. To get incremental gain, you want the source to be grounded, whereas here, what is happening? I mean, this voltage is actually not incrementally grounded. It is some large number multiplied by the incremental voltage at the drain. Okay, that's something that you certainly don't want. So, any suggestions on how I might be able to avoid this? Okay, so one suggestion is to say, you want, for incremental signals, you want this node to be connected to ground. So, put an infinite capacitor here. Are there any problems with this solution? What are the problems with this? Does this work? What did we say was an op-amp? What is an op-amp? It's a voltage controlled voltage source. So, if you put a capacitor across a voltage source, what happens? If you put anything across an ideal voltage source, what happens? That element has no effect on the voltage at all. So this circuit will merrily continue to do what it was doing earlier without the infinite capacitor. So what should I do? Any suggestions? Incremental signals, you want this to be cut off. So there are several ways of doing it. One way is what this chap pointed out there, which is add an infinite inductor here, which will cause this path to become open for incremental signals, and this chap will cause this node to become a short, okay, to ground for incremental signals, thereby realizing the incremental equivalent circuit. And as we have discussed before, infinite inductor is a problem. So what we could do instead is use a large resistor, Rx, let me call this. Still the same common source amplifier that we have been discussing, okay, but it looks very, very different now compared to what the various circuits that we have seen. This just goes to show that there are any number of circuits whose incremental equivalents can all be the same. They just look very, very different. Now, if the circuit was given to you, the first thing you would want to do would be to find you want to find the gain, alright, but before you find the gain, what should you do? Operating point. So let's try and take this whole thing upside down and try and compute the operating point. For operating point, what all go away? For computing the operating point, what is the circuit? This goes away, this goes away, this goes away, because there is no current flowing through this capacitor anyway, and this is what the circuit reduces to for computing the operating point. and this potential becomes VDD times RB by RA plus RB. By analysis, you figure out this is a negative feedback loop, so we use the standard rules for the op amp, which are the two terminals of the op amp input must be identical, or the quiescent potential at the drain must be equal to Vref. What is the quiescent potential at the source of M1? Okay, what is the drain current to the MOSFET? Iref. And let's say that Vref is greater than Vb minus Vt. So the transistor is established to be working in saturation. Alright. So what happens to, so the current through the transistor is Iref. So what happens to, how would I find the gate source voltage? VGS of the transistor is nothing but Vt plus square root of 2 Iref by mu n Cox W by, which means what is this potential? What is the potential at the source of the transistor? Is Vg minus Vgs, which is simply VDD times RB by RA plus RB minus Vt minus square root of 2 Iref by mu n Cox W by I. Now can you tell me what the potential here is? The current through the drain flows like this, it's Iref, that has to flow into the op amp. So this current is Iref. So this potential is simply, if I call this S, is Vs minus Iref times Rx. And then for the incremental equivalent, you can simply, go back to the original circuit diagram, short all the capacitors, open all the current sources, open all the inductors if any. And what would be the incremental equivalent for the op amp? The op amp is basically a voltage controlled voltage source, so that will still remain. Vref will become ground. This completes 3 of the 4 ways of stably biasing the transistor, where the transistor quiescent current remains independent of Vt of the device. So the first way was compare current in the drain, apply corrective feedback at the gate. The second way we discussed was measure the current in the source and apply corrective feedback at the source. This is the third way, where we measure the current in the drain and apply corrective feedback at the source. And the fourth way would be to measure the current, monitor the current in the source and apply corrective feedback in the gate. So this I will leave it to you as an exercise to work out. You can go through the same logical steps and you should be able to come up with the circuit on your own at this time. How is it that we didn't, we didn't need an op amp in the first 2 cases, but now we do need an op amp? Very good. Okay. So what he points out is that in the first 2 cases where we measured the current in the drain and applied current correction at the gate, when we did the comparison process, the voltage at the drain was increasing, which also happened to be the same direction in which the gate had to be moved. So you could do without an op amp. In this case, if ID is less than Iref, the drain potential here goes up. But if you are interested in controlling the source has to move in the opposite direction. So you need some kind of black box which will take something which is going up and make it, and the output must go down. Okay, so you need some kind of inverting amplifier for the drain variation can be coupled to the source. And clearly you see that when we went through the whole argument, the op amp inverting terminal has to be connected to the drain. Okay, so that the direction is the right. So as I said, the fourth variant, it's now I've done 3, so the fourth should be quite straightforward. I will be happy to chat with you offline if you have any issues. That kind of completes the discussion on stable biasing of transistors, where the quiescent current is somewhat well controlled and is independent of the threshold voltage of the transistor. And as we go along in this course, there will be the opportunity to we'll also